What if the deepest, most fundamental rules of our universe weren't invented? What if they weren't meticulously crafted in a lab, but just found by accident in a dusty 200-year-old math book? Well, that's pretty much the bizarre origin story of string theory. It's one of the most ambitious, most mind-bending ideas in all of physics, and here's the crazy part. Nobody was even looking for it. It was like a symphony that was just discovered by chance. So let's dive in and see how this all happened.
So here's the core idea, and it's actually beautifully simple. What if everything, every single particle, every force, everything you see and interact with, isn't actually a solid little point? What if instead it's a tiny, vibrating filament of energy, just a little string? In this kind of cosmic orchestra, different vibrations would create different particles. It's just like how different vibrations on a violin string create totally different musical notes. A C sharp isn't a G, right? Same idea.
All right, so how on earth did anyone stumble upon this whole cosmic symphony thing? Well, back in the late 1960s, believe me, physicists weren't looking for a theory of everything. No way. They were laser-focused on a much more specific puzzle. They were just trying to understand the strong nuclear force. Basically, they were trying to make sense of all this chaotic data they were getting from particle accelerators that showed how these particles called hadrons were bouncing off each other.
And the breakthrough? It came from a place you would never, ever expect. So it's 1968, and this young physicist, Gabriele Veneziano, he's just flipping through an old math book, and he finds this 200-year-old formula. And by just sheer dumb luck, it perfectly described the particle data he was struggling with. Wild, right? But then it gets even weirder. 2 years later, 3 other physicists, Nambu, Nielsen, and Susskind, they all independently have the same incredible realization. They figured out that Veneziano's formula wasn't describing little points at all. It was describing the interactions of tiny, vibrating, one-dimensional strings. And that was the birth of what they called the dual resonance model, the very first whisper of string theory.
This quote just nails how strange this new theory was. See, it was mathematically rigid, like super rigid. Normally when physicists have a new theory, they can kind of tweak the parameters, change a particle's mass here, an interaction strength there. It's standard practice. But with this thing, if they tried to change anything, the whole theory just collapsed. It was like it was either completely 100% wrong or it was completely 100% right, with absolutely no wiggle room. It wasn't something they built, it was something they unearthed, like an archaeological find.
Okay, so they've got this really elegant, even if it is super rigid, idea. And they call it bosonic string theory. The math was beautiful, no doubt, but it came with some predictions that were, bizarre, to put it mildly. In fact, instead of describing our universe, the theory seemed to just fundamentally break it.
This theory had 3 massive, show-stopping problems. Problem number 1, it predicted these things called tachyons, particles that travel faster than light. That's a huge no-no, and it points to a really deep instability in the very fabric of the universe. Problem 2, it only described force-carrying particles, the bosons. There was literally no room in the math for the particles that make up matter, the fermions. And finally, number 3, for the math to even work, to be consistent, the theory required a frankly absurd number of dimensions.
And what was that absurd number? Get this, 26. Yeah, the theory only worked, the math only held up, if the universe had 25 dimensions of space and 1 of time. For most physicists, this was it. This was the final nail in the coffin. It was a fascinating little mathematical curiosity for sure, but there was no way it could possibly describe our world.
But, of all those problems, this one was the absolute killer. You've got a supposed theory of physics that can't explain the existence of a single electron, a single quark, literally anything that you and I are made of. Imagine that. A universe made up only of forces with no matter at all. It was a total deal breaker. End of story. Or so they thought. But just as this whole idea was about to be tossed on the scrap heap of history, a new and incredibly powerful concept emerged from the world of theoretical physics. And this one idea, it would save string theory from being forgotten and transform it into something much, much bigger.
That game-changing idea was supersymmetry. So what is it? Well, supersymmetry suggests there's this profound link, this deep, fundamental symmetry between the 2 big families of particles. You've got the particles of matter, the fermions, and the particles of force, the bosons. Supersymmetry says that for every fermion out there, there has to be a corresponding boson partner, and vice versa. They're basically 2 sides of the very same coin.
Now, this wasn't just some neat little idea. It was a full-on rescue mission.
Because when physicists tried weaving supersymmetry into string theory, poof, the biggest problems just miraculously vanished. Those pesky mathematical instabilities that led to tachyons, they canceled each other out. Gone. And most importantly, the theory could now include fermions. Matter was officially allowed back into the universe.
So, just by adding supersymmetry into the math, physicists transformed the failed bosonic string theory into the much, much more powerful super string theory. This new, deeper symmetry balanced the equations in a really powerful way. And hey, as a little bonus, it even helped with the dimension problem. It reduced the requirement from a totally wild 26 dimensions down to a slightly more manageable 10.
So, great, the theory was reborn. But here's the thing. For about a decade, almost nobody cared. It was just this obscure little pet project for a tiny handful of super-dedicated physicists who just refused to give up on it. They were totally working against the grain of the entire physics community.
And you really get a feel for the attitude of the physics establishment back then from this one story. Leonard Susskind, he's one of the founders of the theory, right? He remembers being literally laughed at by the famous Nobel laureate Murray Gell-Mann just for even bringing it up. It was seen as a complete dead end, a fringe idea that wasn't worthy of any serious attention.
But that small group just kept plugging away. And as they did, they had this absolutely stunning realization. They had been looking at the theory all wrong. This thing wasn't describing the strong force, not at all. It was describing something far, far grander, gravity. They had accidentally stumbled into a potential theory of quantum gravity. I mean, the holy grail of modern physics.
And here's the truly mind-blowing part. Gravity wasn't something they tried to jam into the theory. It just fell out. The mathematics of superstring theory demanded that a certain massless, force-carrying particle had to exist, and when they calculated its properties, they were stunned. It was a perfect match for the description of the hypothetical graviton, the quantum particle of gravity. This was huge. For the first time ever, a theory that started with quantum mechanics had produced gravity, not as an add-on, but as a totally unavoidable consequence.
Okay, so this all comes to a head in 1984. At the time, all the other attempts at a theory of quantum gravity were hitting these mathematical brick walls called anomalies. Basically, their equations would just break down and spit out nonsensical, infinite answers. But then two physicists, Michael Green and John Schwartz, they made this historic calculation, and they proved that superstring theory was mathematically consistent and completely free of all those theory-killing anomalies. All of a sudden, the joke theory wasn't a joke anymore. It was the only game in town, and that was the start of what we now call the first superstring revolution.
You can just imagine it. Hundreds of physicists literally dropped what they were doing and flocked to work on string theory. It was a massive triumph, but it didn't lead to a single, simple answer. Oh no! Instead, it opened up a whole new can of worms, revealing a new layer of complexity and some really, really deep new puzzles.
So, what was the first big surprise? This. Instead of finding just one single, consistent version of superstring theory, the one theory of everything, they found 5. Not 1, 5.
Yeah, you had type 1, type 2a, type 2b, and these two others called heterotic string theories. And the thing is, every single one of them was mathematically consistent. Each one described a slightly different universe. And that was a problem, right? If this is supposed to be the fundamental description of our reality, why on earth are there 5 different versions? Which one is the right one?
And of course, let's not forget the elephant in the room. The dimension problem was still there. Superstring theory still needed 10 dimensions, 9 of space, 1 of time. But we clearly only experience 3 dimensions of space. So, where are the other 6 hiding?
Well, the proposed answer is this idea called compactification. The thinking goes like this. The extra 6 dimensions are curled up or compactified into an incredibly tiny, complex shape. And they're curled up like this at every single point in the space that we know and love. One type of shape that fits all the mathematical rules are these incredibly beautiful, super intricate structures called Calabi-Yau manifolds. And that led to the final dizzying puzzle of this whole era. See, it turns out there isn't just one way to curl up those extra dimensions, not even close. There are tens of thousands of possible Calabi-Yau manifolds, and each one of those shapes results in a universe with slightly different physical laws. The theory gave them absolutely no way to pick which one was the right one.
And that's really where the first revolution left us, not with 1, but with 5 potential theories of everything, an unresolved mystery of 10 dimensions,
And this landscape of thousands upon thousands of possible universes, all hidden away inside these tiny, curled-up shapes. The accidental symphonies had become way more complex than anyone could have possibly imagined. And it left physicists scratching their heads, wondering which of these paths, if any of them, actually leads to our reality.